So we have just defined stress, and we have known that stress is the intensity of internal forces. So based on this definition, we can calculate the numbers, the values of stresses. It would just equal to internal force over area. But to correctly calculate the values of stress, first of all, we need to identify the type of stress we're calculating. Then we need to find the correct area we're using in the equations. Okay, so here we will talk about three different types of stresses. The first one is called normal stress. Then the second one is shear stress. And we have the third type, which is called bearing stress. Okay, the normal stress is defined here. So consider a rectangular bar subjected to an axial force. It's directed along the longitudinal axis of the member, as shown here. So this is so here is the P. Right, it's it's directed along the longitudinal axis of the bar here. Then cut the cross section at AA. The cross section is shown here, and the equilibrium of the lower portion is attained by a distributed force, which has a resultant force F on the exposed cross section, and the F is here. Okay, so the second diagram is a free body diagram. So based on statics, you should easily derive that a equilibrium equation says negative F plus P equals 0. So you can calculate that F equals P. Right, so this is the internal force. Then based on the definition, we can calculate that the average normal stress, sigma average equals F over A. More strictly speaking, the stress need to be calculated using the second equation, but that is too complicated in some of the cases. So in mechanics and materials, a 2000 level course, we just use the third equation. We only consider the average normal stress. So sigma equals F over A, and F is the internal force, and A is the cross-section area. And you can see here the normal stress is the intensity of internal force perpendicular to the cross section. So in this case, the cross section AA is here, AA is here, and your force F is perpendicular to the cross section. So this is a normal force. So let's give a simple example. So here in this example, a solid 0.5 inch diameter steel hanger rod is used to hold up one end of a walkway support beam. This is the support beam we're talking about. Right, then the force carried by the rod is 5,000 pounds. Determine the normal stress in the rod. Okay, this is a very simple case. As you can see here, if we cut this bar out, according to the description, the force carried by the rod is 5,000 pounds. This is here, and then if we need to determine the internal force. Okay, cut a cross section here, get a free body diagram. You get the internal force here. This is F. Okay, so very easily you can determine that the F internal force equals the external load, that is 5,000 pounds. Okay, our definition said that the normal stress sigma equals F over A. So then you just need to find the correct A. And the A here is the cross section, where the cross section is here, and the A equals pi over 4 times d squared, and the d is 0.5 inch. Okay, to put them together, you will see we calculate the A, pi over 4 d squared, and you get a number, and then the sigma equals F over A and then you can just do a calculation to get the results. Okay, this is the result we obtained, and approximately it equals 25 KSI. Then the second type of stress is known as shear stress. Different from the normal stress. Normal stress is the intensity of internal force perpendicular to the cross-section, but shear stress is the intensity of internal force parallel to the cross-section. So how could that happen? Consider a simple connection where the force carried by an axial member is transmitted to a support by means of a solid circular. Solid circular pin. This is a single shear pin as shown in this example here. So this is the pin we're talking about. And if you look at this view in the second diagram, you can see that these two parts, this support, and both the support and the plate would carry the same force, F, and F is transmitted through a single shear pin. And this is the only and here is the only cross-section, the only one cross-section carrying the shear force. Okay, so that is why we call it a single shear pin. Okay, you can only find one cross-section that carries the shear. Okay, the free body diagram is shown here. So to write an equilibrium equation, you would just get negative V plus P equals 0. So you can get V equals P. Right, so this is the internal force, internal shear force in this pin, okay, not in the plate. The stress is the intensity of internal force, so average shear stress on the transverse cross-section of the pin. We're talking about this cross-section. Okay. So it can be calculated by the first equation, the average shear stress, and we use tau to denote shear stress. And we use a sigma to denote normal stress. So the tau average equals the shear force, internal shear force V over the cross-section area, AV. So more strictly speaking, this equation should be, the equation to calculate the stress should be this one. But again, this is complicated in some cases. So in mechanics and materials, we only consider the average shear stress. Just use the third equation. And we use tau equals F over A. And here, more strictly speaking, here, this F should be V, and the V equals P. Okay, example regarding shear stress. Here we have the chain members 1 and 2, chain number 1 and chain number 2, connected by a shackle and a pin. So if the axial force in the chains is P equals 28 kilonewton, and the allowable shear stress in the pin is tau allowable equals 90 MPa, to determine the minimum acceptable diameter D for this pin. So this is a simple design problem. We will talk about more details about this type of calculations in chapter 2. So here we just go through it briefly. Okay, so first of all, let's look at the connection. If you look at the connection here, you will see that you can find more than one cross section that is carrying the shear to transmit the force from one chain to the other chain. Okay, you can find two cross sections carrying the shear. So one on the top and the other on the bottom. So the free body diagram is shown here. So we call this kind of pin double shear pin. Okay, this is different from the previous one. In the previous example, we have just a single shear pin. In that pin, you can only see one cross section carrying the shear, but here two. So we call it a double shear pin. Okay, according to the free body diagram, we can write an equilibrium equation that would be negative 2v plus p equals 0. And v will be half p, right? That would be 14 kilonewton. Then if we know the size of the pin, we know the diameter of the pin, so we can calculate its area. And A equals pi over 4 times d squared. Then you use V over A and you can calculate the shear stress. But this is not the case in this example. In this example, we didn't give you the diameter of the pin. Instead, we'll give you the allowable shear stress in the pin. That is the maximum allowable maximum value of the shear stress in this pin. Okay, but we can also write this V over A equals tau, and if the tau equals tau allowable, then you can calculate the A, determine the area from V over allowable shear stress. Right. Then you can derive from the A, you can derive the D, the diameter. Right. So this is the overall pathway to solve this problem. So as shown here, you can see we derived that V equals 14, and we use this equation to derive the area. And is this the maximum area or minimum area that we should use? So this should be the minimum area, right? The larger the area, the safer the pin will be, the connection will be. Okay, so this will be larger. This will be the minimum value of area. So from this equation here, you should know that the true area should be larger than the calculated value. Right? So based on that, you can determine the diameter of the pin, which should be not smaller than 14.07 millimeter. The third type of stress is a special one, which is called bearing stress. You can see here, this is the third type, a special category normal stress. Its nature is a normal stress due to compression. Okay, due to compression at the interface. The compressive normal stresses that occur on the surface of contact between two separate interacting members is called bearing stress. So this type of normal stress is defined in the same manner as the normal and shear stress, say force per unit area. So therefore, the average bearing stress, sigma b, is expressed as sigma b equals F, that is the force acting on the interface, over the area AB, the contact surface, the area of the interface between two members. So the bearing stress, I highlight that bearing stress is the normal stress acting on an interface. Okay, the distribution of bearing stress on a semicircular contact surface, more strictly speaking, let's see this example here. This is a single shear connection, single shear pin. Okay, so we're determining the bearing stress at the interface between the pin and the plate and the hole of the plate. Okay, the cross section, the interface is shown here. So more strictly speaking, the shape of this interface is a semi-cylinder. Okay, so do we use the P over the area of a semi-cylinder to determine this? We should not do that, because on this interface, the P is not perpendicular to this semi-cylinder surface. So if you use the P over the actual surface area of this semi-cylinder surface, you will not get normal stress. Okay, so to simplify this, we only consider, as shown here, we only consider the projected area of the contact between the plate and the hole or a pin. Okay, so what is the projected area? What is the projected area in the direction perpendicular to the loading direction, perpendicular to the P? Okay, the projected area is shown here. This this transparent gray color thing is a rectangle. Okay, so it's a rectangle with here the size is D and here the size is T. Okay, so the effective contacting area or the projected area of this semi-cylinder shaped interface will be this rectangle, and its area AB is D times T. Okay, so this is the projected area. An example here, this is a straightforward example. A 2.5 inch wide by 0.125 inch thick steel plate is connected to a support within a 0.75 inch diameter pin. So the steel plate carries an axial load of 1.8 kips to determine the bearing stress in the steel plate. And we simplify this this problem in this way. So we use the projected area only of the contact between the plate and the bolt. Okay, the actual area again is here. Right? It's a semi-cylinder, but as we mentioned previously, we only need to use the projected area. In this image, it is the red colored rectangle, and its size will be 2.5. No, it's not. It will be the diameter of the pin 0.75 times the thickness of the steel plate. Okay, that is 0.125 inch. Okay, so we just determine the area first, D times T, that is 0.75 times 0.125. And then you use the F over AB to get the bearing stress at this interface. Then a further example, this is not a bolt. In this example, we're dealing with a tube, a pipe, and a steel plate and a concrete slab. We just stack these three things together, and to analyze the bearing stress, you just need to find the correct interface, contacting areas between different components of this system. And here, this steel pipe column, 6.5 inch outside diameter, 0.25 inch wall thickness, supports a load of 11 kips. The steel pipe rests on the square steel base plate, which in turn rests on the concrete slab. So step A, we determine the bearing stress between the steel pipe and the steel plate. This is step A. We determine the bearing stress between the steel pipe and the steel plate. The pipe is here, and the steel plate is here. So to determine the bearing stress between them, we just need to find what is the contact area between them. So what is the contact area between this pipe and this plate? It will be a circle, right? The external diameter of the circle is given to 6.5, and the wall thickness is 0.5. So the internal diameter will be 6.5 minus 2 times 0.25, and it will be 6. Okay, so the internal diameter will be 6. Then we can calculate the area of this circle, right? So that would be pi over 4 times external diameter square minus internal diameter square. So you will get a result. Then the bearing stress between the tube and the plate will be just the loading, 11 kips over this area. So you will get the result. Now let's look at step B. In step B, if the bearing stress of the steel plate on the concrete slab must be limited to 90 psi, what is the minimum allowable plate dimension? A, the minimum allowable side length of this steel plate. So this is the inverse calculation. So first of all, you can list this equation here. Let's find the contact surface first between the steel plate and the concrete slab. So what is that? In step B, the contact area AB equals, right, the interface between the steel plate and the concrete slab. What will it be? What is this area? It will be the same as the area of the steel plate, right? That will be A times A, right? Or A square, right? Then we know the loading, since we ignored the self-weight, so the loading will still be 11 kips. Okay, so the stress, the bearing stress, can be calculated as 11 kips over A square. Okay, since we have known that the limit of this stress is 90 psi, so this would be not higher than 90 psi. Then you can calculate the A square and then A. Right? So this is the pathway. So as shown here, we list the equation here first and then calculate the AB, and we say that AB equals F over sigma B. So you will get 11 kips over 90 psi. That will be 122 square inch. So that is A square. Right? So this is AB here is A square. Then A will be just 122 square root 122.222. Right? That is approximately 11. Okay. So the size of the plate will be larger than 11.06 inch.